Okay, so here's where we were last time. We were talking about applications, various different applications of Gauss's divergence theorem. Well, let me go back a couple of pages here. One of the first applications we did a bunch of stuff about fluids. Let's not go back to that. But we talked about how Gauss's divergence theorem can apply to gravitational fields. Gravitational fields specifically being this. Right. Okay. Well, it turns out, detailed calculations and setting things up, very carefully, exactly the right way. There's a sequence of results that come out from careful applications of the divergence theorem. First, just a direct calculation. You can compute the divergence. It's 0. It's remarkable. Not at the origin where the mass is, of course, right? The model is non-physical there. The vector field is undefined. We can't talk about what's happening at where the mass is. Nevertheless, the fact that the divergence is 0 everywhere else has powerful consequences. One of them, let's not go through all of them again, but the eventual punchline is, if you have a surface and you'd like to know the flux of the gravitational field created by the mass in the vicinity of that surface, pause. What an overwhelmingly intimidating question. We've got lots of mass all over the place, each particle of which is creating its own gravitational field. Oh, nightmare of complexity. Then I want to talk about how do those vector fields all add up? And then what's the total flux through some lumpy, weird, yet unparameterized surface? Is insurmountable seeming question. And yet the answer turns out to be really, really simple. Nice little formula. It pretty much, other than some constants, it only depends on how much mass total is inside of your surface. I don't even care where it is. I don't care how the density is arranged. Whatever the total mass is, that's all that matters. It's a shocking result. Related, take this equation, divide by volume on both sides, and again, set up appropriately. You can argue that then the divergence of the gravitational field is, again, a proportionality thing. There's a constant. Memorize the constant, negative 4 pi g. It's a constant times density. Right? So, terribly, terribly difficult seeming question. Monstrous vector field. But its divergence? It's just whatever the density is right there. That's what the divergence is. With a minus sign and other constants, again, because of the details. Okay, so we saw this remarkable fact, and then we observed that, hey, electric fields, it's a very, very different physical thing, very different physical phenomenon, involves different aspects of matter. Right? Not all matter has charge. But coincidentally, as it turns out, electric fields are structurally identical. Gravitational fields. Yeah, different constants out front, sure, right? But it's still what you might call inverse square radial, just like a gravitational field. And so other than the constants changing, everything else works out the same. Just like with gravitational fields, the divergence is 0, obviously away from the origin where the charge is. As relates to real physical distributions of charges, same list of results, same 2 punchlines. Flux is proportional to simply the total charge. As it turns out, it's not mass, it's charge for electric fields inside of your surface, and divergence is proportional to charge density. By the way, there's a nice, let me go back to the mass stuff. I'm going to try to be brief about this. Oh gosh, it's really easy to get into a very long discussion on the following point, but I do like to point out that this formula here suggests a point of view on gravitational fields, and that is that flux is created by mass. Right? Wow, that's kind of a weird point of view. That whenever you have a mass, then that mass, whatever surface encloses it, the amount of flux of the gravitational field created by that mass, it just depends on the mass. So the mass is what's creating, you could take this point of view. It's as if, anyway. It's as if the mass is creating flux. in proportion to, locally, the density of the flux that's being created is proportional to the mass density. And there's a metaphor that this suggests. It sort of suggests, and if you want to talk about this, come to my office hours. It's a really interesting conversation, but there's a lot of details. It's as if each little piece of mass is shooting out a fluid of some sort, right? I mean, after all, that's how we think of flux. We think of flux as some sort of a fluid passing through a surface. So it's as if mass is flinging fluid of gravitational force or something. And so, therefore, whatever surface contains it doesn't matter if you have a small surface, if you have a big surface, whatever the surface is, as long as it's containing that mass, it's going to catch all that fluid that the mass is flinging out. So it's as if that's the case. So this is kind of, I'll say, suggestive of the idea that gravity is communicated by little particles, a flowing fluid of little particles called gravitons. So just from the math, just from the way sort of the algebra works out, and the way we're thinking about these objects as pertains to this particular physical quantity, it's kind of raised eyebrow makes you wonder, this lines up just as if these little particles exist. So maybe they do. Anyway, it's a point of view. This doesn't prove squat, but it's a nice point of view. Again, if you want to talk about that more, come to my office hours. I really enjoy it, but it's not required. Okay. Here is a wonderful application of these ideas. I'm going to present this application in the context of electric charges and electric fields because it's a little bit easier to relate to, perhaps. I don't know. Again, it doesn't really matter if we're talking about an electric field or a gravitational field structurally. They're the same thing, right? Electric fields and gravitational fields, it's just different constants. The physical world, of course, they're different, but mathematically, they're basically the same. So let's think about a charged sphere. So we have charge uniformly distributed over a sphere like this. Right? And let's ask the question, what is the electric field that this distribution of charges creates? Now, I remind you, what a terribly intimidating question, right? We've already agreed that little particle of charge right there, well, that creates its own little electric field. Right? This little particle over here, color choices, this little particle over here, it creates its little electric field. There's bazillions of little particles there, each one of which is creating its own different electric field, right? I mean, this electric field here created by that red particle is different. It's not the same as this electric field created by that little particle. They're sort of centered in different places, right? They're kind of, they're analogous, right? But they're different field vectors at different points. If you want to add all of those up over all of the bazillions of particles over this entire sphere, seemingly intractable question. All right, so a wonderful thing happens, though, as it turns out. Let's see if I can erase all these little bits, this mess that I created here. Oh, gosh. I always create these little challenges for myself. Got it. Okay. So I want to talk about what is this actual electric field that's created, and it turns out that with powerful tools and careful, clever reasoning, we can answer this question. All right, so here we go. By the way, we're specifically going to be looking at the electric field inside of the sphere. There is a revised, kind of slightly different, but morally, strategically similar calculation you can do outside of the sphere. That is a fantastic exercise for y'all to think about on your own. But anyway, we're just going to talk here about inside of the sphere, and let's consider some specific point inside of the sphere. Not all the way, not on the actual surface, but well comfortably inside the sphere. And I'm going to make a couple of plausible suggestions. First suggestion I'm going to make: grand total at that point, the electric field's got to be what I like to call radial, right? I mean, this is just an intuitive plea, but the sphere itself of where the charges are distributed, that sphere is symmetric. It's rotationally symmetric. If you take a uniformly charged perfect sphere, if you rotate the sphere itself, nothing really happens. It's still a uniformly charged sphere, even if you rotate it. So how could the field not be then also radial? Right? It doesn't make any sense. So I argue that it's got to be on axis like that. Furthermore, if I were to look at any point, reminder, we're looking at this point here on the surface of the sphere. If you look at all these other points, equally distant from the center, well, the field not only has to be radial at all of those points as well, but furthermore, these magnitudes have to be the same, right? That magnitude's got to be the same as that magnitude. It's got to be the same as that magnitude. Just a symmetry plea. If the sphere is symmetric, how could the field be lopsided? Right? Which way would it be lopsided? Would it be stronger, longer field lines over on this side? What distinguishes that side? Right? It just kind of can't be. Okay. All right. So let's study this field then. And keep in mind, my goal is to understand the field itself. I'd like to understand what this is. As is very commonly the case in math, I'm going to learn about something I'm interested in by considering something else related to it. And this is what I like to call a mathematical bank shot. Right, we're going to get at understanding the field by understanding something that's not the field. So, for that in mind, for reasons that have not yet become clear, I would like to ask the very different question, what is the total flux of that vector field through this inner green sphere? Now, do keep in mind, the charge is still all out here. That's where the charge is. I've picked a point on the inside, picked this point here, that point. That point defines equidistant points there that makes a sphere, this green sphere. I want to talk about the flux through the green sphere. Okay. All right. So, now, good news. I can tell you exactly what the flux is through that green sphere. I can compute that flux through the green sphere two different ways. On the one hand, we've already made an argument that this field strength is constant. Right? And the field is perpendicular to the surface. And so grand total, the total flux, easy calculation, right? That flux is equal to the magnitude of the electric field times the area. Yeah? I mean, in other words, the dot products are the cosines are all one here. All the field lines are perpendicular. They're therefore parallel to these normal vectors, and so just magnitude times area gives you flux. But now let me give you another calculation of flux. Using this formula here, electric flux. You say you have a surface, a boundary surface. You want to compute the flux? Well, it's the total enclosed charge times some constant. Total enclosed charge. How much charge is there enclosed in this green sphere? The answer is none. There is no charge in there. All the charge, as we previously discussed, all the charge is out here. Right? There is no charge on the inside. So if there's no charge, then there is no flux. And what does that tell us about the electric field? It tells us that the electric field, that thing right there, it's got to be zero. Right? What is it I can multiply times area to get 0? Well, 0 is the only answer. Everybody see how that works? This is really slick. This is a very clever, creative application of ideas to allow us to draw a conclusion. By the way, also a remarkable conclusion if you think about it. What we've agreed now is that if you look at this point right here, that point's not in the center of it's somewhere kind of in the interior, but it's not at the center. So it's closer to these charged particles, which are pushing one direction. It's farther from these charged particles that are pushing the other direction. There are more of these charged particles that are pushing that way. There are fewer charged particles pushing that way. It's like we have it's like a tug of war kind of a situation. There's a smaller number of stronger, because they're closer, charged particles over here, right? And then there's a larger number over here pushing weaker because they're farther away. It's like we have a tug of war between 3 bears and 1,000 squirrels. Who wins that tug of war? I don't know. Right? So the amazing conclusion that we get here is that, grand total at this point, the electric field is exactly 0. It's a perfectly matched tug of war between these two different sides. It's just wonderfully elegant how nicely this works out. How we doing? Everybody okay? Now, again, how did we draw this conclusion? Did we write down all of the electric fields created by individually each one of these particles over here and each one of these particles over here? Did we write down all of the individual electric fields? Hey, don't forget about these. There's particles over here, too, pushing every which way at our point of interest. Did we write down all of the electric fields and add them up? Brute force? Oh, no. Oh, my gosh. I guess maybe I could do that, but it's overwhelmingly scary. No, we made some super careful, clever arguments that fundamentally make use of this consequence of Gauss's divergence theorem. Right? So Gauss's divergence theorem is what allows us to really draw this conclusion. Yeah?
How did you conclude that the inner flux?
Yeah, because flux is proportional to charge. And there is no charge inside of this inner sphere. Here, let me get my picture back. Inside of... I used bad color choice. Here, I'll do this. Inside of the sphere, the charge is 0. And all the charge is out here. Charged particles are on the outside of the sphere like that. So in that, inside of the sphere in question, there's no charge in there. If there's no enclosed charge, then there's no flux per this corollary of the divergence theorem. Anyway, I think it is a pretty cool example of, why is the divergence theorem so useful in physics? Stuff like this. Right? This is crazy powerful. And then by extension, I know there's not as many physics majors in here as engineering majors, but engineers, you're going to use a lot of physics, right? I guess depending somewhat on what part of engineering, but lots of engineering uses a lot of physics, and stuff like this is all over the place. Okay. All right. E&M, Maxwell's equations. This is a neat thing to talk about. Now, this is not a physics class, so I can't spend as much time on this as a physics class would. But recognize this formula that we've talked about. This is, divergence of the electric fields proportional to charge density. We wrote this down last time. Okay. There is a kind of a parallel kind of fact about magnetic fields that says this: the divergence of a magnetic field is 0. Again, this is not a physics class, but that's what we're going to work with. The electric and magnetic fields, what we have here are statements about their divergences. Okay. All right. There is there's a label that we put on these equations. These are called Maxwell's equations. These are two of what you might call 4 Maxwell's equations. There's another 2 of the 4 that we'll talk about later. We're going to develop some more mathematical tools first. So these are what you might call the first 2 of Maxwell's equations. But more specifically, these are certain versions. Each one of these equations, there's kind of 2 versions of it. There's a differential version. Now, why do we call these differential versions? Well, you can see it right here. These are called differential versions because we're talking about derivatives of these electric and magnetic fields. Divergence is computed with derivatives. Okay, so that's the name. Okay, well, it turns out that there are what are considered to be integral versions of these same equations. And I'm going to come back to that terminology after we see how this works. But here's how you connect the two. I'm just going to talk about electric fields here. The magnetic field, the calculation on the magnetic side is parallel. Okay, so here's divergence of the electric field is charge density. You'll note there it is in this calculation again. And I note that is a critical step in drawing this connection to flux of the electric field being proportional to charge. So this blue equation, which I've kind of recopied down here, but yeah, whatever. This blue equation, you can see, makes use of that green equation. Now, how does the argument work? How do we go through this blue argument? Not a lot going on here, really. Flux. That's the formula for flux. Let me say yada yada yada. We'll come back to that in a second. We rewrite this triple integral. That's just a rewrite using the green equation. Total integral of charge density gives us charge. That's just a density argument. That's not really a thing. Not much going on there. Right? So the one step that I just glossed over is that one. The one sort of non-trivial step in this argument is making the connection that a flux is a triple integral of divergence, namely Gauss's divergence theorem. Right? It's just straight up, like right down the pipe, Gauss's divergence theorem. Right? Okay. All right. So, like I say, what we have is these 2 different versions of what we call 2 different versions of the equation. We have the blue version is the integral version, as I like to call it. The green version is the differential version. You can see that we already talked about the differential version involves derivatives. Well, the integral version involves integrals. Right? This is a flux. Flux is an integral. Right, so the names are pretty natural. Now, there's a temptation to say, why don't we just call these different equations? They're clearly different. These 2 equations are not identical. Not identical is called different. Right? So what's this idea of saying there are 2 different versions of the same thing? Well, there's a couple of different ways to say this. But for one thing, look how close the connection is between them. Right? Using the green theorem to prove using the green equation to prove the blue equation is a couple of lines. So they're very closely connected. But even more than that, let's read through these. I mean, just semantically, how do these roll off the tongue? This says flux is proportional to charge. The green one says flux density is proportional to charge density. Other than that word density, they both say flux is proportional to charge. They're talking about very much the same things. Slightly different points of view on exactly the same thing. One is talking about densities, namely sort of locally in any given vicinity. What's the relationship? The other is talking about globally, accumulated over an entire region. How do these things relate to each other? But they're both talking about the same thing. So this language is extremely common, talking about the differential versions of the theorem differential versions of the equation and the integral version of the equation. I think it's very important not only recognize that, just if only culturally, that that's how you're going to hear them, but it's important, I think, to realize how why that makes sense, why this is a very reasonable thing to call these equations. They are two different versions of the same thing, and seeing that they are two different versions of the same thing requires using the divergence theorem. So this is another tremendously valuable application of Gauss's divergence theorem. The math that motivates this whole discussion, Gauss's divergence theorem. Tremendously valuable application there. It's, giving you, linking points of view on seemingly otherwise very different statements. Okay. All right. Same story with magnetic fields. I'll let y'all think through this argument. It's very, very parallel, and for y'all to think about on your own. Okay. Let's talk about Gauss's divergence theorem in R2. Just a quick reminder: everything we've been doing with Gauss's divergence theorem has pertained to solids. Three-dimensional solids and their boundary surfaces. Given a solid, you look at the boundary surface, you think about a flux through that boundary surface. And we eventually then related that back to a triple integral on the solid. So this has been an unavoidably R3 discussion to this point. So is there a two-dimensional version of this? So a reasonable question, if you've got a region like this region here. Let's just say you could talk about its boundary curve. We can define boundary for the purposes of this discussion, oriented outward. Right? And we could reasonably ask, okay, given some vector field, now this is in R2, so the vector field that we would look at here would represent a two-dimensional fluid flow. So, think about wind on the surface of the earth, or migration pattern of birds or wildebeests or whatever, something like that, but something that's intrinsically two-dimensional. Right? And we could ask, if we're interested in the flux, given some vector field, some non-constant vector field, we could talk about, can we relate the boundary flux here, namely, how many birds are flowing into our region, into and out of, net. What's the bird flow out of our region? Can we relate that boundary flux to some integral over the solid, over the two-dimensional region? So the way we're going to approach this is to view this as an accumulation. So first of all, does this flux accumulate? Got to draw the usual picture that we draw. Let's think about flux through that boundary. Right, don't forget boundaries are oriented outward. We can talk about flux through this boundary. Don't forget boundaries are oriented outward. Right? And if I were to add the purple flux to the blue flux, would I get the flux through the boundary of the sort of the union? Right? So it's our usual accumulation question, and the answer is yes. You can probably see that coming. Why would I be talking about it if it doesn't work? Right? But pretty easy to see why. In all of our cases that we've considered that are kind of along these lines, no pun intended, what it comes down to is you got to look on the shared pieces of boundary and ask, is there a cancellation? And yeah, there totally is. Let's look at, along this, I keep hitting the wrong tool. On this piece of boundary, as part of the boundary of this region, the orientation is that way. As part of the boundary of this region, the boundary is that way. Oh man, I hit the wrong here. And so thinking about a flow, well, a flow like this, right, let's look at that vector. the flux out of D1, that dot product, compared to the flux into D2, that's that dot product. And you can see they're exact negatives of each other, and of course they're exact negatives because the orientation vectors are exact negatives of each other. Said differently, all, sort of mathematical constructions aside, every time a bird flows out of D1 through this edge, that bird unavoidably flows into D2 through this edge. Yeah? Everybody see what I'm talking about? So, in terms of net bird flow, nothing's happening on that edge. The birds are just kind of moving around inside of our union. Right? So we have an accumulating quantity. We go through the usual algebraic arguments. Here's the statement that the boundary flux accumulates. Boundary flux has this accumulation feature, just like all of our previous contexts. Was that a hand or? Yeah.
Why is this different from the last time we?
What's that?
Why is this different from like the last time we proved the same thing?
Oh, well, now it depends on what you mean by the same thing. You mean the three-dimensional version? The 2D1. You mean Green's theorem? Yeah. So Green's theorem was not about flux. Green's theorem was about circulation. So on Green's theorem, we were thinking of the orientation on the boundary being along the curve in a with a certain convention, and then those are the two orientations that we were comparing. These two orientations like that. And so they're still opposites. They still cancel, right? But they cancel here because they're parallel to the surface in different directions, whereas over here they cancel because they're perpendicular to the curve, but in different directions. Look, you're quite right. The origin of your question is the fact that these are so terribly analogous. Yeah, absolutely. Different in the details, different in the applications. Okay, so boundary flux accumulates, multiply and divide by area. There's a double integral. What is this integrand? In the limit, what does this turn into? A bunch of details I don't want to talk about. It's just details. You can show that that's equal to this expression. And what we have here is another accumulation theorem that boundary flux through the boundary curve of this two-dimensional region is a double integral over the interior. Now, we have seen this equation before, super quick. I'm just going to give you all a reference. I'm going to ask you all to flip back in the notes to note where this came up before. When we were looking at Green's theorem, we made this, we talked about flux through a curve at that time, and we turned this question, you may recall, we're like, well, this vector is 90 degrees from our tangent vector, and so we made a clever argument about how you can just turn your head to the side, and all of a sudden that becomes a TDS instead of NDS. You adapt appropriately, and then you plug it into Green's theorem, and it works out to give you the same thing. But we had this very different point of view on it at the time. We viewed this as a corollary of Green's theorem. Here, we are making our own completely independent accumulation argument to come at this same result. Okay. Alrighty. Okay, so moving along now, going into the last section of the book. Very exciting. Stokes' curl theorem. Let me take this opportunity to remind y'all, it is the last section of the book, but it's not the last section we'll be looking at. We are going to have to go back to chapter 13. Remember back in chapter 13 we kind of skipped all that optimization stuff. The case that I made as to why we needed to skip the optimization stuff was that chapter 15 has a lot to talk about. There's a lot to digest in chapter 15, and I want to get that done as early as possible to give y'all as much time as possible to let those ideas kind of settle in. You got to get used to, it's got to feel good. You got to let that have time to really gel in your minds. So that's what we're doing now. That's why we're doing chapter 15, kind of early, if you will. So we got to go back to chapter 13 and do optimization. But anyway, this is the last chapter we're going to talk about in chapter 15. And it's just, we're going to go back to our diagram. Let me get to here it is. Here's our diagram. We've covered most of this diagram at this point. These two little boxes down here are just kind of notation representing that whole business about everything having a lifetime of 2. So we made the observation, for example, that a gradient has curl equal to 0. If the curl is equal to 0, then that means that there is an anti-gradient. Remember, we talked about those results a long time ago. I gave you some geometric intuition for why that should be, why that morally kind of ought to be true. Likewise, we haven't done this yet, but a curl must have its divergence equal to 0. And if a vector field has divergence 0, then it is a curl of something. I have not given you any geometric or intuitive plausibility argument for that yet. I'm just asserting it at the moment. Okay, nevertheless, we've talked about those results. We talked about the fundamental theorem of line integrals. We have just recently talked about Gauss's divergence theorem. And remember, I made this case that if you take a gradient and do a line integral, if you take a boundary and evaluate the corresponding function, you get the same thing either way. Notice we have the exactly analogous result over here now. Gauss's divergence says if you take the divergence of a vector field and compute a triple integral, as opposed to if you take the boundary of that solid and over that surface compute a flux, you get the same thing. Structurally, they're really, really analogous result. Now, geometrically, they're very different, right? The fundamental theorem of line integrals is about line integrals over curves and how you can evaluate by plugging in a magic anti-gradient function into the endpoints. Right? Gauss's divergence theorem is something about fluxes of surfaces and triple integrals over solids, and geometrically very, very different, but structurally, wow! Oh my gosh! They're just analogies are overwhelming. Okay. So now remember, I've made a very vague reference. Best that we can really do in this circumstance. Can't talk about the actual details of this, but I claim this is not a coincidence. This happens. This crazy analogy happens because these are special cases of the same theorem. It's not a coincidence at all. There is a single theorem of which these are both special cases, and there is another special case that we're going to talk about. Oh, by the way, likewise, Green's theorem, all same pattern, of course. The other special case we're going to talk about is what we're going to do now. It is Stokes' curl theorem, and what it says is that if you have a vector field and you compute the curl of it and do a flux of that curl, why would do such a thing? I don't know, it seems weird. But likewise, if you take that surface, look at its boundary curve, do a line integral of your original vector field over that boundary curve, those two integrals are going to end up being the same. Same pattern, structurally the same sort of kind of result in a very, very different context. So that's the next thing we're going to talk about. Very quickly, I do want to point out that it does seem a little out of order. Why did we do this first and then this second to leave the one in the middle third? Why would we do that third? Shouldn't we do that one second? Shouldn't we kind of increase the dimension a little bit each time? Why did we kind of skip a dimension, as it were? And it's hard to see this coming, but it turns out that there's some little annoyances, some little issues of orientation that are just make Stokes' curl theorem a little bit more delicate. And it's just easy. It's better to go into Stokes' curl theorem having seen more examples of the pattern beforehand. That's why. I think the vast majority of books do it this way. Okay, so here is our situation. We are... go back to it here. We are looking at a surface we're going to need to talk about its boundary curve. And over that boundary curve, we're going to be computing a line integral over that boundary. Don't forget we have a name for that. Line integrals over boundaries we call circulations. Right? So according to the structure that we have set up in the diagram, that's what we're going to, that's the object in which we hope to find pattern. Right? So this, again, doesn't prove anything. I'm just saying, the diagram suggests, hey, this is, start moving in that direction optimistically. So that's why we're going to do what we're about to do here. Back to it. Here we are. We have a surface. We're going to consider surfaces in R3. And we're going to think about their boundary curves. Okay. All right. Now, awkward. Boundary. It's a curve. It's a curve in space. But curves in space, we need to talk about orientation. If you're going to talk about line integral on a curve in space, line integral which direction? Right? We've faced this problem before when we were doing Green's theorem. We look at two-dimensional regions. They have a boundary curve. But when you say circulation, do you mean circulation this way? Or do you mean circulation that way? They're negatives of each other. You got to decide. And said differently, we have to make a choice of a convention. What does this word mean, boundary, as relates to orientation? We made a arbitrary choice on this with Green's theorem. I suppose we could have gone either way, right? Clockwise, counterclockwise, whatever. We made an arbitrary choice. We arbitrarily chose to get on board with what everybody else does in the world, right? So, arbitrary but reasonable. Likewise here, it's arbitrary, but oh man, really reasonable. It's just everyone else does it this way, and so that's why we're going to make the following choice. But it is arbitrary. Here's how the choice works. Imagine a surface, and by the way, I mean your surface is here like this or something. It's up in space, all bent around. It's really hard to draw a picture of that. So forgive my artistic incompetence there, but try to visualize something along these lines. We have a curve in space. Okay. That curve in space. To that curve in space, there is a boundary curve. There's that boundary curve. And our question is that boundary curve oriented that way or this way? Right? Which is it? We want to know an orientation on that boundary. Well, here's the thing. The surface is oriented to. Right? So that ends up being really important. If you want to know the orientation on the boundary, well, you need to know what is the orientation on that surface. So our surface floating up here in space, it's not just a dumb surface. That surface comes with an orientation. Side note, we know eventually we're going to end up talking about a flux. Flux through this surface. If you want to talk about flux through a surface, you've got to have an orientation. Do you mean flux, as you might say, upward through this surface? Or do you mean flux downward through this surface? They're not the same thing. Okay, so we have an oriented surface. Here's the rule. Given that oriented surface, that orientation is described by a normal vector. The rule is as follows. Take that orientation vector, specifically find a point near the boundary. Now, very importantly, not on the boundary. You can't put it on the boundary. Just go near the boundary. Near the boundary, we're going to create what I like to call a swirl. This is just for geometric sort of intuition. This is not rigorous. By a swirl, I mean imagine like a little whirlpool kind of a situation going around that normal vector. The swirl is computed is identified as follows. Again, this is arbitrary. This is the arbitrary choice that planet Earth has gone with. Thumb of your right hand. Put that in the direction that the normal vector points. Your fingers, then, of your right hand, they kind of curve around in a certain direction. Right? This is entirely, this is a means of communicating an arbitrary choice based on the fact that our hands pretty much all work the same. Right? So thumb in the direction of the surface's normal vector. The fingers then sort of curl around. You'll notice they sort of curl around the thumb in a well-defined way. That's the way that the swirl goes. And then notice that swirl. This swirl here, it sideswipes up against the boundary in a well-defined direction. That swirl sideswipes up against this boundary that way, not this way. Yep.
Does the boundary curve need to be like closed, like a loop?
Yeah, it's a nice fact about boundary curves is they are all closed. If you think about it, I mean, how could a boundary curve end? Right? If the boundary curve ends, then how could it be a boundary? Because it's like the surface would have to kind of go all the way around it or something. Yeah, boundary curves don't ever have ends. Boundary curves are always closed. Yeah, great question. Yeah, but it turns out that it addresses a problem that never comes up. Yeah. Okay, so it's an arbitrary choice, but there it is. Okay, and as we previously discussed, the quantity that we are fingers crossed hoping is going to end up having the accumulation feature, the quantity we're looking at is boundary circulation. It's just like in Green's theorem. Just like in Green's theorem. In fact, the conclusion that we're about to come to is very often thought of as Green's theorem in space. Okay, so boundary circulation around boundaries of three-dimensional surfaces. And here goes our calculation. Now, this is my hilariously bad attempt to draw a surface up here in space. All right, I apologize, but you try it. It's really hard. But anyway, so here's my depiction of a surface like this. The surface is an oriented surface. So this surface here is oriented. I'm depicting the orientation with these normal vectors. Okay. And question, if I were to take this surface and cut it with a pair of scissors, and if I were to think about two questions, on the one hand, on this piece of surface, if I were to look at the appropriately oriented boundary circulation, and if then on this piece of surface here, if I were to look at the appropriately oriented boundary circulation, is it the case that the sum of those individual circulations, does that add up to give you the boundary circulation around the union? In other words, does boundary circulation have this accumulation feature? And look, as in all the examples we've seen so far, what that comes down to is, on this shared piece here, on that shared piece, do you get cancellation? And well, thought of as part of here's our shared piece. Thought of as part of the I'm not going to do the algebra. Thought of as part of the boundary of this side, the orientation is that way. Thought of as part of the boundary of this side, the orientation is that way. On that piece of curve, then, we're going to have two different line integrals along the exact same curve with exact opposite orientations. And so they cancel. Right? And this is morally the same argument that we made with Green's theorem. Just, in fact, you could literally take a picture of I encourage you to try this. Take a physical page with the argument that from our lecture notes, how I argued this with Green's theorem. A physical page of that, pick that page up, do it like that, maybe tilt it whichever way you like, what you then have is a good three-dimensional picture of how this argument works in space. It's the same argument, just lifted up and kind of bent. Okay. All right. You can write it down algebraically. The punchline is you get integrals over C3 in two different directions, and they cancel. Okay. All right. Again, you can write it down algebraically, but the intuition that I think is easier to work with is the fact that you get the two opposite orientations on each sort of appearance of this line integral. Okay. Okay. So boundary circulation accumulates. The total, the boundary circulation around the whole thing, the whole surface, is the sum of the boundary circulations around the individual pieces of surface. That's what we mean by an accumulating quantity. We make our usual argument. We multiply and divide by area. Notice that I then have a surface integral. It's all over but the shouting, kind of. You can see a surface integral showing up, right? So a line integral has turned into a surface integral. We just have a couple of details to work out, and that is what is this limit, and why didn't we get a flux? Right? If you look back at our diagram, we were expecting to get a flux, not a scalar surface integral. How are we doing? Is everybody on board? Okay, and I seem to have completely lost track of the clock. It is now a minute over time. So this where we're going to have to call it for today. We will pick up here on Monday. Y'all have a great weekend. Don't forget to turn in your homework. And also, some of y'all came in after I started lecturing, so make sure that I mark you down on attendance. I'll start going through that right now.